So you guys can see that okay?
Yes.
Yeah, great. So I have a I have a new cable today to get rid of that terrible problem. I'm trying a new cable that uses a different port on my computer. I think the port on my computer was faulty and glitchy, and that's what was causing that problem with all those interrupts last time. So we'll see if it works this time, the new cable. So far so good. Let's see. So we're still a little bit early, a minute early. When you guys come into the session, are you guys on mute? Like when you join this?
No.
It depends on your personal Zoom settings.
I thought that I had done that, so you people would come in on mute, but you guys, when you come in, you're not on mute. Is that correct?
I'm not, yeah.
Yeah.
How do I change that? Can I just change that? I have forgotten how to change personal Zoom settings. Shoot. Well, I'll try to figure out how to change that. Okay, folks. Well, let's get this show on the road. Today, so let's begin. Shoot, it's recording, right? I started the recording already. Today the main event is to discuss diffraction. So that will be the big topic for today. But let's just mention a few things about what we talked about last time. Last time we were talking about consequences of periodicity. And solid state physicists love periodicity. And so that this is sort of like the way to sort of picture it in your head, or at least how I like to picture it in my head. You know, we have a lattice, a real space lattice. I'll try to, just draw a little lattice here in real space. And so all these lattice vectors, I can think of them as some set of lattice vectors, right? And I'm drawing the lattice vectors as points on the lattice, the way you see here. But now I can also associate with this lattice as a reciprocal lattice. And I can think of all the reciprocal lattice points, G, that are the reciprocal lattice vectors. And the reciprocal lattice is also some kind of lattice. But the units are 1 over distance. And so this leads to momentum. You can think of these as momentum. And the reason is because the reciprocal lattice is the set of G vectors corresponds to a set of waves. And those waves, e to the I g dot r, are periodic in the lattice. So last time I gave you some formula for calculating. So if I give you the real space lattice, you can calculate the reciprocal lattice by plugging into a formula. But what you should be thinking in your head is that all those reciprocal lattice points correspond to wave vectors. So G is a wave vector. And these wave vectors then lead to waves that are periodic in the lattice. And so a nice way to visualize it all in your head, the way I like to think of it is you draw the real lattice, and then let's draw the inside. You can think of the reciprocal lattice as a set of arrows. And those arrows represent the G vectors, the wave vectors for all the waves that are periodic in the lattice. So because if G is a wave vector, then we have, remember, momentum is equal to H bar K. And so then whenever someone talks about a wave vector K, we always think of it as momentum, right? So the reciprocal lattice is this set of momenta. So the G equals a set of momenta that is fixed in the lattice. So if I rotate the lattice, then I rotate those arrows, they're kind of fixed in the lattice. It's like, so every lattice is like two lattices, the real space lattice and then this set of this momentum lattice, and that's the reciprocal lattice. So it's sort of like a porcupine, like I got my crystal lattice and there's all these arrows sticking out of it. So think of a lattice really like a porcupine. It's got these little spiky things sticking out, and that's the reciprocal lattice. At least, and the reason why I like that picture so much is that picture is, you might wonder, why do I have that weird picture in my head? Because this is the picture that comes from diffraction. And we will soon discuss. So you will see why this picture that I just described is actually a very intuitive picture, which kind of comes from diffraction, although it might not seem intuitive right now. So, okay, so now let's talk about diffraction. And diffraction, you guys already know of something about diffraction. Like if I have planes of atoms, then you guys know from other classes that, if I have two beams of light, and I did this last time, but I'll just remind you, like a beam of light there, and then if I have another beam of light coming in like that, then if I have, beam 1 and beam 2 of light, and they're bouncing off these two planes of atoms, and if the atoms are a distance d apart, then you can do this little trick that you all have seen a million times. I got a right angle there, a right angle there, and I can look at this path difference, which is d. If this is theta, that angle, then this is theta here, and then this is d sine theta is that, and this is d sine theta. And so path difference for the two beams of light, 1 and 2, is equal to 2d sine theta. And then you get diffraction when 2d sine theta is equal to an integral number of wavelengths, where that's the wavelength of the light coming in like that. Okay, and this is the wavelength of the light going out. Okay, and so that's a condition for constructive interference. Constructive interference for the rays 1 and 2 at the detector, where there's some detector here. I'll put it here. This is the detector far away. Okay, so that's a picture that you guys have all seen. And so now I'm going to generalize the exact same picture, but now I'm going to make it more general. So now let's do a 3D generalization of this very simple picture. 3D generalization. And that will lead us to the concept of diffraction. And so for the 3D generalization, what we do is, let's first mention this concept of that you guys have already heard of somewhere in some class. It's this Higgins Principle. And this concept of Higgins Principle is simply that if I have some extended object, and I bathe it, and I shoot a plane wave at it. Now the plane wave is coming at it. You know, like this is the plane wave is like, I can draw it like that, but a plane wave is actually planes of constant phase. So this is another way of drawing a plane wave. Planes of constant phase. Bathe this object, but then every little part in the object will then radiate in phase with the wave that's hitting it. So the idea is that every little part of this object will become a radiator. And because the idea is that it's scattering. So the object scatters the light. That's sort of the modern language that we use. It's scattering. And so every point on that object is going to scatter the light at the same phase as the light that's hitting it. So scattered light has same phase as incident light. And that's a very important concept. And so hopefully you've heard it somewhere before. That's Higgins Principle. So now let's use this to understand diffraction for a periodic crystal. So before we go into and talk about the periodic crystal, let's just consider the most general case. So let's shoot X-rays at an arbitrary density of electrons. So this is density of electrons. Okay, so let's do that. And so let's do it like this. So let's assume that this is my density of electrons described by, I'm just trying to think the best way to draw it so it'll be easier for me later. I'm just gonna redraw it. It's better if I draw it big. So this is my N of R. Okay, so that represents some big blob of electrons with some arbitrary electron density. And so now I'm going to have an X-ray source here. It's a machine that you can buy. It's not that expensive. I forget how much they cost. Maybe $10,000, $20,000 for an X-ray source. I forget. X-ray source. Okay, and so this X-ray source is shooting X-rays at my electron density, okay? And this is meant to be waves. And these waves have, the X-rays are described by a wave vector K. And those X-rays are coming at my thing. So these are plane waves. Okay. So those are X-rays coming at my electron density. Plane wave. So my X-ray is equal to a plane wave. And then and then I have a detector. And it's my X-ray detector. And then the question is, the question is that we're going to answer is question, what is the intensity of X-rays at the detector? That's the question that we want to answer. And to do that, what we're going to have to do is consider interference of the X-rays, because they're going to interfere with one another. So to do this, let's consider what we're going to do is let's add up the rays. And so this is what I mean by that. Let's consider 2 points in this electron density, 0.0, and another point will be point R. So this is 0 is the origin. And then this is the and this is R. And so we're going to consider what happens when the X-rays that hit, the X-rays that hit 0, I can draw them as like this ray. So that's the X-rays that hit 0, and then those X-rays, they're going to scatter into my detector along that path. But then some of the X-rays will also, because it's a plane wave, are also going to hit this. And so I got to draw it parallel. And so those are the waves that hit the point R, and they also will be scattered toward the detector. So let's just consider the X-rays hitting these 2 points in my electron density. Now, of course, what I'm going to do next is I'm going to generalize that to all the points, but let's just consider these 2 points. So point 0 and point R. Now, I want to know what is the interference of the X-rays that emanate from these 2 points. And so to do that, I can draw this construction, because I can draw a perpendicular line here. And I can then draw, oh, I'm not drawing it too good. I'm sorry, I'm gonna have to, let's redraw that. Because I need these to meet at these points. Sorry, I just needed to get this to look right like that. And then to look like that. Yeah, okay. So now let's do this construction. So I can draw a perpendicular line there. And then I can draw another perpendicular line here. And then I notice that this is, I'll call this delta x1, and I'm going to call this delta x2. And so what I want you to see is that the path difference, the path difference of the 2 rays is equal to, well, can someone tell me what is the path difference between those 2 rays as they hit the detector?
Delta x1 plus delta
1 plus delta x2.
Yeah, exactly. Delta x1 plus delta x2. And so then I can say that the phase difference, well, actually, before we talk about the phase difference, that's what I want to get next, is the phase difference between the 2 waves at the detector, But before we get the phase difference, let's just remind ourselves of part of this geometrical construction, which is that this X-ray going in this direction has a wave vector k, and so I can write this k as equal as the magnitude times the direction. I'm going to call the direction n hat. So n hat is a unit vector pointing in the direction of the incident X-rays, incident wave. I'll call it the incident wave. Okay, so k is the magnitude of the wave vector of the X-rays. You know, k is just 2 pi over lambda, where that's the lambda is the wavelength of the X-rays. Now the scattered wave is going to be going in this direction, which I'll call k prime, some other direction. It's arbitrary. The k prime is some arbitrary direction into the detector, and k prime I'll say is equal to the magnitude k prime times n hat prime. Okay, so this direction here is n hat prime going in this direction to the detector. So, and this I'll call the scattered wave. Scattered wave, because it's a wave of X-rays. It's an electromagnetic wave. X-rays are electromagnetic waves. Okay, so now I want to ask you a question. What Now, obviously, obviously K does not equal K prime because they're different vectors, they're pointing in different directions. They're different. But let me ask you this question. What's the relationship between K and K prime, the magnitudes? Can someone tell me? Is there a relationship between the magnitudes of K and K prime? Well, let me say something else. Let's say that the scattering off the electron is elastic. What does elastic mean?
No
Someone-
energy
The
loss.
energy is saved.
Exactly.
Oh,
Yeah, that's correct. Energy is constant. That's right. There's no energy loss in the scattering. Okay, so, and this is true. When an X-ray hits an electron, usually it's elastic. It bounces off elastically. Usually, sometimes it doesn't, but usually it does. Okay, so now that you know that's elastic scattering, tell me what's the relationship between K and K prime?
they are equal.
Yeah, exactly. Because the wavelength lambda is the same for the scattered wave and the incident wave, 2 pi over lambda. It's the same, right? So that means that I can say that the magnitudes are the same. Even though the vectors are different, the magnitudes are the same. That's very important. Okay, so now so now you know then that the phase difference, if I have delta x1 plus delta x2, then I can get the phase difference by multiplying that distance by a wave vector, which is simply, I'll call it K, right? So that's the phase difference. And so that's going to be the key thing that determines the interference properties of this. Okay, so now what we have to do is find delta x1 and delta x2. So let's look at this delta x1 right up here, and I can see that I can see that I have this direction n hat, and I have this vector r. And so using this r and this n, and here here I have the vector n hat prime going in this direction. Okay, so using r and n, what is delta x1? Can you do the geometry in your head? Look at this picture I drew. I have delta x1, I have r and n. What is delta x1 equal to in terms of r and n?
It's R dot product with N.
That's exactly right. And you can just see it by looking at it, by the construction. That's right. But now let's do the same thing for x2. And so now for x2, I have r, and now I have n hat prime. So what is delta x2? What is delta x2 now equal to? And this is the direction of these little delta x's. Can you see that in terms of r and n prime? What is delta x2 equal to? Can you tell me?
I think it's pretty the same. It's R dot product with N prime.
Yes,
Or do we
except for one
have
slight difference.
minus
Minus.
Exactly. Very good. Perfect. That's exactly right. And so that means then that the phase difference of those two rays at the detector is equal to, it's going to be K times R dot n hat minus R dot n hat prime. Okay, do you see that? That's the phase difference of the two waves, those two rays. And so then what I can do is I can say, well, that's equal to, I can do it like this. I can do it, that's equal to R dot K n hat minus k n hat prime, right? But and the phase difference, I'll just call it delta phi. But what is k times n hat? Well, maybe that's a trick question, but that's just the incident wave vector k. That's the definition. See, I have it written up there. That's k. And what's k times n hat prime? Well, that's just k prime, right? I mean, I have those relationships written up top. And so then that leads then to this very cute relationship, which is that the phase difference between the waves hitting those two parts is going to be r dot k minus k prime. And so what that means then is if I generalize this into the idea of Higgins, from Higgins principle, that what that means then is that my total electric field, which is going to be equal to the electric field of wave 1 of ray 1 plus ray 2, is going to be proportional to the electron density, because the amount of scattering depends on the electron density, but then I also have to take into account this wave. So the wave hitting 0, the point 0, this will be point 0, and this will be point r, is going to be proportional to the electron density at point 0 plus the wave that comes from the electron density at point r. And so because from the Higgins principle, the electric field is going to be proportional to that electron density, because if there's more electron density, there'll be more scattering. So that's a very simple relationship. But there's one difference, which is that the wave that's coming from point r has a phase difference, e to the I delta phi. And that is the essence of diffraction. That is the key. That's the key point to understand. All right. Whoops. Okay. And so that's going to be the total. That will be the total E field at detector, or what I will call is the amplitude. Since the intensity is equal to that thing squared, intensity is equal to E squared. So the total amplitude of the electric field of the X-rays at the detector is going to be proportional to this quantity. So what that means then is that if I want to know, that's the total amplitude due to the sum of those two waves. But now let's consider all the waves, because the X-rays are a plane wave that's coming in and it's hitting all the electron density at the same time. It's bathing the whole electron density. So every point of the electron density is emitting. And so now I can say the total amplitude of X-rays at the detector due to entire N of R, I just have to add them all up. And so it's just going to be this. It'll be, I'll call that F. I don't know why they use F, probably means something in German. F, and I'll have a subscript K and another subscript K prime. And this total amplitude, which I'll call FKK prime. And the reason I call it KK prime is because that's my initial direction on the right, and that's my final direction on the left. And those of you who have taken, quantum mechanics, which is supposed to be all of you, this is sort of familiar from, well, if you've taken 137B, it's the from Fermi's golden rule or the Born approximation. This is a very common notation to write it like this. So that's the total amplitude of the X-rays at the detector. And then I just have to add up all the waves that are landing at the detector. So this is for the volume of the electron density of the electron density. And I have to write, then I'm going to have to write, it'll be N of R times E to the I, and then the delta phase for each ray coming from each R. And then this is integrated over R. Okay, so that's the total amplitude of all the X-rays hitting the detector. But now I can plug in this expression because now I know what this phase difference is. It has this very beautiful, simple little expression for the phase difference the phase difference that each source of electrons has relative to the origin, relative to that one. That's just our starting point. And so this is going to be, because I know that this thing is going to be R dot K minus K prime. So now let's write that. So I can then write that my total amplitude Fk prime K is equal to the integral over the volume of N of R times E to the I K minus K prime dot R d cubed R. Okay, well, that's a very cute little expression. It's not hard to derive, really. It's like the understanding is maybe a little, you have to understand the geometry, but the math is actually fairly simple. But there's something really cute to notice. So I'm going to write that right here. And there's I want you to take a look at that because I want you to notice that I could rewrite that. There's something very beautiful about the structure of this integral, which is that I could write it like this. I could write the e to the minus I K prime dot R N of R. And remember the intensity of the X-rays. The X-ray intensity at the detector is proportional to F squared, FKK, right? Because it's going to be the electric field squared. And you might be wondering why I don't make this a vector quantity, because it's the polarization of the electric field that makes it a vector quantity. But the scattering preserves the polarization. So all the scattered waves have the same polarization. So that's why I can just ignore the polarization. They all have the same polarization. It's all the same vector. So I can write it like this, e to the I, e to the I K dot R d cubed R. And this is a really cute thing because I want you to notice that this has the same structure as in this is the same as in quantum mechanics, because in quantum mechanics we have this very similar problem where we say, hey, we have a potential V of R and we shoot in a particle with some wave vector K, and then it scatters into some angle defined by K prime, and we call this angle theta. And then we ask ourselves, what's this? And then we have this thing called the scattering amplitude, which we call F of theta. And the scattering amplitude in the Born approximation is very simple. Born approximation, we can write it as K prime V of R K. It's this matrix element. And this is a very famous result, because if you write out that matrix element, if you write out, using the rules of quantum mechanics, then that becomes, this is the initial state, and this is the final state, and that becomes e to the minus I k prime dot r. That's the initial state. I'm sorry, that's the final state. And then v of r is the potential, the scattering potential, and e to the I k dot r is the initial direction of the particle. And so that's the initial direction, and that's the final direction, d cubed r. And I just want you to see that these are the same integrals. Look at them. So what we just did this very simple little wave Higgins principle classical. I know what we're doing, the diffraction is a classical thing. I'm just shooting waves at an object and just seeing what the scattered waves do. But I want you to see that we end up with the exact same expression that you get from quantum mechanics using the Born approximation, using all the fancy rules of quantum mechanics, Schrodinger equation, and blah, blah, blah. And the reason why it's the same, you get the same result, is because in quantum mechanics, we're also just doing wave scattering, but now you have a quantum wave that hits a scatterer, and then you have the scattered wave. So I just want you to, the point I'm trying to make is that a wave is a wave is a wave. It doesn't matter. It's a quantum wave or classical wave, whatever. It's just a wave. Water wave, doesn't matter. It's just a wave. Waves are waves, and you get the same behavior. And so it's really quite beautiful. These are the same. Oh my God. So we're getting the same behavior, the same. Oh, let's see. What I meant is that one is the same. Those integrals you'll notice are the same integrals. Okay, but let's not get too sidetracked by quantum mechanics, but I just want you to see that, because in quantum mechanics, remember in quantum mechanics, then you have the probability, which is like the cross section goes as f of theta squared. So in quantum mechanics, you have the probability, but for X-ray diffraction, you have intensity. So it's kind of like in quantum mechanics, you have probability, but for X-ray scattering, we have intensity, but they both are sort of mathematically identical quantities, and the math is all the same. Okay, so enough of that. But now let's take a closer look at this scattering amplitude for the X-rays, the amplitude for the X-rays to scatter into the detector. And let's notice something. Let's use the fact. Now let's use the fact. Let's use the fact that the electrons that it's a crystal. So then N of R is periodic in the crystal lattice. Okay, we're going to use that fact now. But if N of R is periodic, then that means there must exist a reciprocal lattice G, and you know what it is from those formulas that I wrote down last lecture, and that you can derive according to that proof that was posted to the website. And if this set of reciprocal lattice vectors exists, then that means that N of R must be able to be written as a sum over all the reciprocal lattice vectors, because the reciprocal lattice vectors are all the possible vectors that are periodic, right? So even though I don't even need to know what the lattice is, I just need to know it's periodic, in which case there exists a reciprocal lattice, and I can write this expression. So I can always write for a crystal, I can write my electron density is periodic in the reciprocal lattice vectors, like that. Okay, so now let's plug that in. Plug it into F, and let's see what we get. Let's do it, and you get something really cute, because let's do that. So let's plug it into the expression for F, and that expression is up there. There it is. The expression for F is going to be the integral over volume N of R, which is now the sum over G, N of G e to the I G dot R. That's N of R, but then I have to multiply by e to the I, the phase difference thing, e to the minus I k minus k prime dot r d cubed r. Okay, did I get that right? Yeah, k minus k prime. Okay, and so then let's just do a little bit of math. Let's just expand that expression a little bit, and let's pull the sum out. Let's pull this. This is not being integrated over. I can pull it out of the integral, and now the integral is an integral over volume e. And let's just rearrange it a little, the exponent a little bit. Let's rearrange it like this: g minus k prime minus k dot r d cubed r. Okay, I just rewrote it ever so slightly. Hopefully that is not confusing to you or incorrect. Okay, so that's the total amplitude of all the X-rays scattered into the detector in that direction, corresponding to k and k prime. K is, remember this is the k is the initial direction, and k prime is the final direction. Okay, but now let's take a closer look at that, because let's remember something. Let's remember a little bit of math. Let's remember something very cute. Let's remember that a Dirac delta function is equal to, and sometimes you get the little 2 pi's mixed up, but it doesn't matter. In one direction, in one dimension, 1 over 2 pi infinite e to the I kx d k. So that's the definition of a Dirac delta function. Hopefully you guys sort of remember what a Dirac delta function is. That means that that's if I plot a Dirac delta function, delta of x, it's a spike at the origin. Okay, but I can do the Fourier transform of a Dirac delta function, and I know that there's also can be a corresponding Dirac delta function in k space, and a Dirac delta function in k space is this 1 over 2 pi integral infinity to infinity e to the I kx d k. I'm sorry, no, oops. D x. Okay, so this is the more important one here. This is basically just saying that if I integrate a bunch of waves, and all the waves have the same starting point, like I got long ones and short ones, and I'm just integrating them all, then if you add them all up, you see you're going to get destructive interference, except at then that's a delta function, so that you're just going to get the spike at k equals 0. Okay, so this is mathematically a delta function in k. So this is something that I want you to remember. All right, and so that means that this integral is a delta function. It's delta of this. See, this is delta of k, which is the thing up here, and so this is going to be delta of g minus k prime minus k. So that's a delta function. That integral is a delta function. And so that means that this integral, this thing, that means that f of k prime k equals 0 unless what? Someone tell me. Because what I've just said is that f, this total amplitude, is it has a delta function in it. And we know that a delta function, let me remind you of a delta function. The definition of a delta function, delta of k equals infinity if k equals 0, 0 if k does not equal 0, and the integral of delta of k dk equals 1. It's normalized. So these are the properties of delta functions that you're supposed to know already, that like you learned in quantum mechanics and other class. And so the point I'm making is that this amplitude has a delta function in it. And so that means that this amplitude is 0 unless what?
G is like the difference between K prime and K.
Unless, say it again, please.
If like the G vector is the difference between K prime and K.
That's exactly right. I need this thing to be 0. I need the interior to be 0. So it's 0 unless G minus K prime minus K equals 0. Because a delta function is 0 unless the thing inside of it is 0, right? Okay, so this is 0 unless that's true, which then leads to exactly what you just said. G equals, or I'm going to write it differently. I'm going to reverse the order. I'm going to write it as K prime minus K equals G. Ta-da! I'll even say it. Ta-da! Because what we've just done is derive diffraction. So that's it. This is the big climactic moment. You're all supposed to think, oh my God, it's so amazing. And so that is the expression for diffraction. Because basically what it's saying is that what this means is that we get destructive interference of all the waves, destructive interference of all the waves except when the directions are perfect, such that the final momentum, when people say k, we often use the word momentum instead of k, but the final wave vector, which sometimes people say momentum minus the initial wave vector, has to equal g. So that means that nothing comes out of the crystal except for at these directions. And so here's another way of seeing it, like, because this is actually really funky, because check it out. Like, this is what you might expect. I send waves at my crystal, and then every atom is an emitter. So they all start emitting, right? And so then you start just getting a big scattered wave like that. And it just goes out continuously in all directions. So you might expect X-rays to be scattered in all directions. This is what you would naively expect. But if you expected that, then you'd be wrong, because what really happens is that I got my crystal and I shoot my plane waves in with my incident K. They bathe the crystal, but then I only get scattered X-rays at special directions. Bing, discrete special directions. What are those special directions? Those special directions correspond to what? Tell me.
Lattice,
Say.
for the reciprocal lattice.
Yes, yes. Because K prime, the scattered wave minus K, equals G, but there's a whole bunch of G's. There are many G's. I have the whole reciprocal lattice. And that's why I like this picture, because basically you shoot in your X-rays and you get, bing, a porcupine. And that porcupine is the reciprocal lattice. So it's like, all you got to do is shine some X-rays at a crystal, and then bingo, you get the reciprocal lattice. It just pops out. And so you just look to see where directions are my X-rays popping out at, and boom, that's the reciprocal lattice. You just get it for free. And that's why, I like to draw the lattice with a bunch of arrows sticking out, because those arrows represent like X-rays that are shooting out of the crystal, because I shoot in an X-ray and I get X-rays coming out, but only in special directions, the reciprocal lattice direction. So it's pretty cool. So that's how you get, so X-ray diffraction. So X-ray diffraction gives you the reciprocal lattice, boom, right off the bat. So that's pretty neat. Okay, let's continue with this. So, but there's a really important point, which is that when we talk about G, we're talking about G for the lattice, meaning the periodic, the periodicity of the crystal. But remember, the crystal, these, so like, this is what I mean. Like I have this, suppose this is one crystal, okay? But now suppose I'll call this crystal number 1. But now let's do this. This is crystal number 2. Okay, I draw, those are 2 crystals. Now, so here's my question to you. Do these 2 crystals have the same reciprocal lattice vectors, yes or no? Yes or no?
Yes.
Correct, because they have the same periodicity, But are these both the same crystal? Yes or no?
No.
That's right, they're not. They're totally different crystals. And yet they have the same reciprocal lattice. So when I shine X-rays at them and the X-rays go ching, sticking out, boinking out into these special reciprocal lattice vector directions, is it going to be the same directions for the 2 crystals? Yes or no?
Yes.
Correct.
I guess.
Correct. Yes. The answer is yes. We just derived it, right? We just
So
have a,
do we have any method to distinguish these 2 crystals?
that's where we're heading right now. Yes, the structure factor. We're about to derive the structure factor. But I just want you to understand the diffraction is the same for the 2 crystals. And yet in your heart, you know that crystals are different. And in your heart, even though you might not know nothing about X-ray diffraction, you know that somehow there's got to be a difference, right? In the X-ray diffraction, like, come on, man, there's got to be some difference, right? And there is a difference. And it turns out the difference is in the intensity of the beam. So what I'll say is these 2 crystals, so crystals number 1 and number 2, they have the same beams. They have the same reciprocal lattice vectors, but they have different intensity for the beams. So the point is then that the basis affects the intensity of beams, okay? So the structure of the basis, because this is the, right, this is the basis. So these 2 crystals are the same crystal structure. They have the same lattice, but they have different basis. Well, one has a 1-atom basis, one has a 2-atom basis. And so they both will have the same reciprocal lattice, the same beams coming out in the same directions, but the difference is that the intensity of the beams will be different. So the basis affects the intensity of the beams, not the number of beams or the direction of the beams, but the intensity. So how does that work? Okay, let's derive it. And so to see this, the way to see this is to derive the structure factor. Structure factor. And the structure factor is S sub G. And let's derive the structure factor now. So the structure factor is, let's do this. Let's suppose that we have some crystal, some weird crystal. I'll just draw it like that. And we shoot an electron in, I'm sorry, we shoot an X-ray in at K. And suppose that it comes out, here's my detector. And suppose that it comes out at some direction K prime. And we know now from the derivation we just did, we know that for this to happen, K prime minus K has to equal what? Tell me. Has to equal what?
G.
Yeah, it has to equal a reciprocal lattice vector G. So let's suppose we pick one particular reciprocal lattice vector. That's like one of the beams, because I got X-rays are going off in all these different directions representing all the different Gs. But let's just pick one particular beam at one particular G. Okay, so then suppose K prime minus K is G. So then we know then the amplitude of the X-rays going into the detector for that G is going to be this. I'm going to say then that F K prime K is equal to, I'll just call it now F of G, the amplitude, since the K prime minus K is G. I'll call it F of G. And that total amplitude, we're just going to use the formula that I had before, right? Where's that formula? I just don't feel like rewriting everything. Well, maybe it's quicker if I do, actually. Yeah, here it is. You see it right there, F of K prime. So I got that. So this, I'm going to make, so I'm going to do that. And now I'm going to make it be equal to the integral of N of R, the electron density, times, but now it'll be E to the minus I G dot R, because that's where I would have had the K prime minus K, which is now equal to G. And now I have to integrate this over the whole crystal. All right, I'm integrating this over the whole crystal. Okay, so that's the amplitude of the X-rays in my detector. And so now what I notice though is we realize that N of R is periodic and E to the minus IG dot R is also periodic in the crystal, because by definition, the G's define waves that are periodic in the crystal by definition. So these things are periodic. So that means I don't have to integrate that over the whole crystal. That means that I can just integrate this over one unit cell. And I could just say, if I'll just say that my total amplitude is N times this integral over one unit cell. N of R, E to the minus I G dot R, D cubed R, where N equals the number of unit cells in the crystal. Okay, yeah?
Is there any question, but is there any, what's the relationship of the electron density with the potential V? Is there any, are they correlated or something?
Well, I mean, we're just assuming that we are assuming Higgins principle. Remember, we have Higgins principle,
Yeah.
which is that the scattered wave is just proportional to N of R. So we're just basically saying, so we're doing this very trivial thing where we're just saying that the scattered wave is proportional to E of R. In other words, if here's a scatterer, I have my incident wave, which is E naught sine K dot R minus omega T. That's the incident wave, right? That's K. And then I have this scattered wave of this point. And so this is sending out waves in every direction. And I'm saying that this wave is going to be, and if that point is R, then this wave will be the scattered wave will be N of R times E naught. I'm keeping the polarization, sine K prime dot R minus omega T. Okay, that's the scattered wave. So this is the incident wave, and that's the scattered wave. Does that answer your question?
Probably. I just noticed that in the formula of Fg, if I replace NR with the potential V, we just get the Fermi's golden rule, and I'm wondering whether there is some relationship between
Yes,
N and
that's
V.
that's the relationship that I described to you before. Like, look back here. See when I drew this and I said the Born approximation?
Yes.
The Born approximation comes from Fermi's golden rule. It is Fermi's golden rule. It's the same thing. Okay, that's like what I was trying to point out before. Okay.
So this N and V is the same thing, right?
Yeah, yeah. I just see it's right here. I said same. See? Same
Okay.
thing.
Okay. All right.
See, I
Thank
got
you.
the V and I got the N, but we're just not using that language, okay? Because
All right.
this is classical. And so the point I'm trying to make is that if you do a classical derivation of diffraction, it's all the same math as quantum mechanics. It's all the same. So that makes it kind of beautiful and kind of cool. Okay, so but let's keep going with the math, all right? And so now let's derive this thing. So now what we see is that we have this f of g, this total scattering amplitude is equal to this thing n, but the total number of unit cells times this integral, but this integral is the structure factor, okay? Where the structure factor S of G is equal to the integral N of R over the unit cell, e to the minus I G dot R. So immediately you can see that S of G is the intensity. This gives the intensity of the beam. S of G gives intensity of the beam at G. And so immediately you can just see from this very simple formula that if I have two crystals with different bases, then they're going to give us, then they're going to have a different structure factor. And so the intensity of the beams will be different for the two different crystals. So if you want to extract the basis of the crystal from your X-ray diffraction, you have to start looking at the intensity of those beams, and you have to sort of work backwards from that using this little formula that I just wrote, this little integral that we just derived. And so there's cute little ways of doing this that X-ray crystallographers have sort of developed over the years. And so let's consider one of those, which is very famous. Let's consider this. Let's consider this idea. So suppose that this is a unit cell. This is my unit cell. And now suppose that I have, let's say I have two atoms in my unit cell. There's one and there's another one. And so let's say that this is the origin 0. Then what I can do is I could say, well, I'll call this atom, I'll say that that atom is at R1, and then this atom. And so if I want to, and so what I can do is, suppose that I want to know, suppose I have two atoms, one is at R1 and one is at R2. But to do this integral, I'm integrating over the whole unit cell. So let's pick an arbitrary point in the unit cell, which is right here. I'll call that point R. And so then let's draw it back. Whoop, 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 whoop. That's R. And so then what I can do is, let's consider each of these atoms as having separate electron density that contributes to that point at R. And so I'll call this rho 1. That's the distance from the center of atom number 1. And this is atom number 2, unit cell with 2 atom basis. And I'll call this rho 2. So what I can do is I can consider I can consider the electron density separately from the different atoms in the unit cell. And so what I can do then is I can consider that the N of R, this is an approximation, but the approximation I want to make is that N of R in the unit cell, N of R is equal to this sum, J equals 1 to P of N J of R minus Rj, where I have P atoms in the unit cell. Okay, so these two things go together. Okay, so I just want you to see the math, you know, maybe sometimes it's hard to follow this math, you know, if it's the first time you've seen it, but I'm just saying that the total electron density is just the sum of the electron density of the different atoms, and I can write it in terms of vectors, these row vectors.
Professor,
yeah.
is this unit cell equals the basis?
R minus Rj. Wait, let me make sure that I have this definition. R minus the what?
I mean, the unit cell, because right now we have two atoms in our unit cell, but I'm wondering whether this is equal to the basis we choose to represent our overall crystal structure.
Yeah, the basis is defined by the RJs. Does that make sense? Because see, in this one example, I have R1 and I have R2, and so that defines my basis. Does that make sense? Does that answer your question?
Yes. Okay.
Oh, okay. All right.
Okay.
So I drew a specific example on the left. Yeah.
The structural factor Sg, when we integrate over the unit cell, is the other G vector also like all the possible G vectors or just the sum?
Yeah. Well, the way to think about it is that every G factor, if I shoot X-rays in, then I'll get a beam of X-rays at every G. So I'm going to get like this huge number of different X-ray beams. And so what I'm going to do is just pick one, okay? And so you pick any one you want. You just say, what is the intensity of this particular beam? Does that make sense?
Yes.
Okay. So that's what this analysis is. We're doing an analysis for one of the beams, an arbitrary one. Okay. So now let's calculate the structure factor using this simple little mathematical definition that I wrote. And so let's plug this in. So let's plug into SG. So I'm going to use this atomic approximation and I'm going to plug it into SG. And so that's going to give me SG. The structure factor for a particular beam of X-rays will be an integral over the unit cell of this electron density, which is now written in this funny approximation, this very simple approximation where I'm just adding up the electron density individually for the different atoms. Okay, and so this is electron density from jth atom is this, okay? All right, and then I have to multiply this times e to the minus I g dot r d cubed r. And then, so what we'll do is a simple change of variables. And we'll say that rho j is equal to r minus rj. And you can look at the picture I drew up above to give you a sense of what the rho j means geometrically. In which case I can rewrite r as rho j minus or plus rj. Okay, just a change of variables. Not super intuitive change of variables, but it works because then using this change of variables, we can write the structure factor. There's a reason for doing all this math because in the end, you get a really pretty little answer. So we can now rewrite this integral as an integral over the cell for the structure factor. And now this electron density, I can write it as an integral over all the atoms in the basis. I mean, a sum over atoms in basis. So it's a sum over all the atoms in the basis, n sub j. Now before I had r minus rj, but now I'm going to replace that with rho j. times e to the minus ig. Now, before I had dot r, but instead of r, now I'm going to write it, I'm going to use my change of variables and replace the r with rho j plus rj. So this is actually kind of making it all much more complicated than it was before, but then it'll look better. It'll all come together in a moment. And my integral change of variables, the r is replaced by rho j. And the reason why I do this is because now this is not integrated over. The rho j is not being integrated. And so I can pull it out. Pull out. And so I can rewrite this as this. I can say I have this sum over j equals 1 to p e to the minus I g dot r j. And now I'm integrating over the cell n sub j of rho sub j e to the minus I g dot rho j d cubed rho j. And this is actually a very beautiful result, because what I've done is this is just a property of the individual atom. This is an atomic property. See, it's an integral over the electron density of the atom, atomic property of one atom. And so I will call it, so this thing ends up getting called F J for the jth atom, and it's for a particular beam, the jth beam, F sub j, F sub j of g, and this thing I'm going to call the atomic form factor. And it's really cute because if you think about it, then that's just Fermi's golden rule, or the Born approximation for a single atom. That's basically the expression you'd get if you analyze scattering from a single atom. And so what we have then is that we have the structure factor, F S sub G, is equal to a sum over all the atoms in the basis, J equals 1 to P, F sub J of G, E to the minus I G dot R J. And so this is a sum over the atoms in the basis, but each atom has its own atomic form factor. And so that quantity gives you the intensity of the beam at G, and that shows you how it depends on the different atoms in your basis. So if you were an X-ray crystallographer, then this is like your bread and butter. This is basically the basis. So this is the basis of X-ray crystallography, X-ray crystallography. Because these are the relationships. Because the thing is, when you do X-ray crystallography, you're shooting X-rays in and you get a bunch of beams, and there's only two things that you can measure in your X-ray crystallography. Is like, what are the directions? You count the number of beams coming out. What directions do they come out? That gives you your G's. And then what's the intensity of the beams? That's all you got. You got the direction and the intensity of the diffracted beams. But from the intensity and directions, you can then go backwards and figure out what is the structure, because you're getting the reciprocal lattice and the basis. The direction of the beams gives you the reciprocal lattice. The intensity of the beams gives you the basis. And once you have the basis and the reciprocal lattice, boom, you get the real lattice. Okay, that's how it works. Okay, so that's crystallography. And so, but let's just, and then some of this will be on your homework, sort of going through that. But let's do something else. Let's consider, so the idea is that, so here's your crystal. I'm shooting my X-rays in with K. I'm getting all these beams of X-rays coming out, And my X-ray crystallographer machine, my diffractometer, will like measure all those beams and tell me the directions and intensities of all those beams. And so these are the, this gives me all the G's. But it kind of depends, you know, but it depends on a few things, because like I could rotate the crystal, right? And so you can kind of see that as I rotate the crystal, it might kind of affect the scattering if I start so if you're an X-ray crystallographer, you're going to take your crystal and you want to really, you know, find all those beams and, you know, all those G vectors. And so you can kind of rotate the crystal around. And so the question is, you know, which beams exactly are you going to see? Because if I just shoot the X-rays in at one angle, I get a bunch of beams. I'm not actually going to get all the reciprocal lattice. I'm only going to get some fraction of it. And so in order to pick up the whole reciprocal lattice, I got to rotate my crystal around. And that might not make sense to you, but let's make it make sense, because the question is, here's the question that we want to answer now. Which G's do we see when we do this experiment? Okay, when we shoot those X-rays in, which G's do we actually see? We actually don't see all of them at once. We only see some subset of them. So which ones do we see? Well, it's just a simple geometrical construction. It's called the Ewald sphere construction. Ewald sphere construction tells you which ones. Ewald sphere construction. It's a simple geometrical trick that lets you know which ones you see. That's really easy. So what we do is, this is the experiment, is I've drawn it, this picture on the left, you know, I'm circling it right now. That's the experiment. And so to understand which G's we see when we do X-ray crystallography, let's draw, first thing we do is draw the reciprocal lattice. Draw the reciprocal lattice. So I'm just going to make up a fake reciprocal lattice and just draw it. So let's say that this is the reciprocal lattice. Okay, now I got a reciprocal lattice. And then second is put your incident wave vector, put the nose of K, your incident wave vector, on a G, a point, a G vector. Okay, so I'm going to, so suppose that this is my K. I'm just going to, so suppose that this is I'm just going to draw, I'm going to just pick an arbitrary case. So suppose my electrons are coming, my X-rays are coming in with this G vector. I'm sorry, with this K vector. So that's my K. So suppose that that's my K vector relative to the reciprocal lattice. Okay, so that's just the direction of the incoming X-rays relative to the reciprocal lattice that is fixed inside of my crystal, relative to my crystal. Okay. And I put that I put my K at the, I put it at the nose, the tip of my K at the nose of my K at one of those vectors. And then third, I draw a circle of radius equals K. All right, so now let's draw that circle. Da, 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 da. I have trouble drawing circles. Okay, that's the circle. You see it? That's the circle of radius K. And then fourth, find the G's touching the circle. Then those are the beams. For example, look, I see Actually, I'm going to redraw. How many? Notice I'm touching this one, and I'm touching this one. I'm going to circle them. I notice that my circle is touching 2 points on my reciprocal lattice. So now, if I draw an arrow to this guy, then this arrow I can call K prime. And so let me make sure that I did that. Oh, I drew this incorrectly. Oh, God damn it. Sorry. Wait, let me make sure I got this. Center. From the center. Wait, let me see. I put it there. I drew my circle. You know, I drew my circle incorrectly. God damn it. Sorry. I did this. I was wondering why it's not working. I have to draw my circle. Sorry, I did this incorrectly. I have to draw my circle starting from the center point right here. And so now I'm going to draw my circle. I'm sorry, I drew the wrong circle. Okay, so I draw the circle from the center point of K. Oh, that's a terrible circle. God damn it. Man, I draw really lousy circles. All right, let's have that be my circle. Okay, so that's a not very much better circle, but it's ever so slightly better. And let's say that I have points out here. And so now what we do is we look for points of the reciprocal lattice that are on that circle. Okay, and so we notice that there's one right here. I will circle it. And so now I can draw this arrow, which is, I'll call K prime. And so the point that I want to make is that from this construction, you can see that if I draw the arrow here, K prime minus K is equal, you can see that it's equal to a reciprocal lattice vector. Because by definition, all the points in that lattice are reciprocal lattice vectors, and every point on the circle has the same magnitude of represents an elastically scattered Xray. And so those are all the possible K primes, but all the possible K primes is on this circle, but the only K primes that get scattered are the K primes that satisfy K prime minus K equals a reciprocal lattice vector. And so then I need so the dots that hit the circle satisfy this relationship. All right, so that's the point. And this might seem abstract and weird to you when you first see it, but now you can see that it's actually quite useful, because now you can imagine that if I change the angle of my X-rays relative to the crystal, what I'm doing is I'm taking this circle, which we call the Ewald sphere, and we're moving it. And as it moves through the reciprocal lattice, the edge of the sphere touches those points. And every time it touches a point, bing, an X-ray starts shooting out at that direction. So so the point is that as I rotate, so the point is that as I rotate the crystal in front of the X-ray beam, that's equivalent to moving this Ewald sphere around, and I'm going to get all these different beams shooting out whenever that sphere hits a reciprocal lattice vector. So in the real world, you're moving the crystal and you're just seeing all these X-ray beams just shooting out in weird directions. But what's happening geometrically is that the Ewald sphere in sort of like this, in this like abstract space, reciprocal space, what's happening is that the Ewald sphere is being swept through the reciprocal lattice. And so that's why X-ray crystallographers want to rotate their crystals all over the place so that they can map out the entire reciprocal lattice. All right, that's how it works. Okay, so sorry for going over a couple minutes. This is a good place to stop. Okay, bye-bye.
Professor, I got a question.
Yeah.
So when we do this experiment, we are we moving the detector or are we moving the incident wave?
Actually, I've never done X-ray crystallography in my life. I have no idea how they actually do it. But I think what happens is, it's sort of like, there's 10 different ways you could do it. I mean, basically, I think there are different types of X-ray crystallography setups, but I think it's common to be quite honest, I think what people do is they grind the crystal up into a powder and they shoot the X-ray beam at the powder because the powder has every orientation in it. All right. So I think in the real world, people prefer to use a powder, and then you have to have the detector. The detectors have to be over a sphere. So you want to like have X-rays in, hit the powder, and then then from the powder you get all the G's, and they're going to hit the sphere, and you need detectors around the sphere. But if you have a single crystal, then you're going to have to rotate that single crystal, and then have detectors placed at your sphere. But the exact geometry of how they do it, I don't know. Maybe I'm sure that some of you guys have done it. Like, has anyone out there done X-ray crystallography? How many of you out there have done X-ray crystallography who are still here? I mean, if you got to leave, just take off. Has anyone done X-ray crystallography of all you guys? Okay, well, you have not?
No.
Okay, well, I guess it's the blind leading the blind then. Oops, jeez, that's really quite annoying. Okay, so yeah, so I'm sorry I can't answer your question better than that. Okay.
All right. That's
Okay.
Good. Thank you.
Okay.
Professor,
Bye-bye.
thank you.
Yeah.
I have another question.
Sure.
How do we deal with like forbidden peaks we cannot see in our diffractogram using this Ewald sphere?
You're asking how do you deal with them?
Yeah, because right now I cannot see the reason why we cannot see somehow like forbidden peaks within our diffractogram, like 100 peaks in our like FCC structure, that sort of thing.
Well, I mean, you're going to have to, if you had some single crystal and you shot the X-rays, you're just going to get a few of the G's, and then you're going to have to rotate your crystal, and then you're going to get more G's, and you're going to measure the intensity of all those G's. And then you're going to have to do an analysis where you work backwards from that to figure out, what is the reciprocal lattice and what is the intensity of all those X-ray peaks. And so so that's what you do. So what is your question again?
I mean, sometimes, for example, if we have like FCC structure, crystals, a crystal with FCC structure, then I think we cannot see like 100 peak in our XRD diffractogram.
Wait, if you have, I don't know why you say you can't see a peak. I mean, if my basis is 1 atom per unit cell, and I have an FCC crystal with 1 atom, let's just have the simplest basis, 1 atom per unit cell, then I have a well-defined reciprocal lattice. And if I shoot the X-rays in, I'm only going to, depending on the orientation of the crystal with the X-ray, the incident beam, I'm going to get a few of my G's according to this construction I just drew. But if I took my crystal and I rotated it around, I would then pick up all the other ones. And so eventually I could sweep through, all the G's. I mean, there'll be some you basically, the reciprocal lattice vector is an infinite lattice, right? So I don't need, but it's periodic. So I don't really need every G vector because it's periodic. I just really need to see, I need to recognize the periodicity, and I need to understand what is the unit cell of my reciprocal lattice. So it's not like we need to pick up all infinity points. So I would just take my FCC crystal and just rotate it around until I picked up a whole bunch of points. And then I would look at those and I'd say, okay, what's the repeating structure? What is the reciprocal lattice? What's the repeating unit in this mess of scattered X-rays?
I see.
Does that make sense? Did I answer your question?
Yeah, for sure.
Okay, good.
Thank you
Okay.
so much.
All right, bye-bye.
So is it,
Hi. Oh, sorry.
Yeah.
I was, oh, sorry, you can go.
Okay, thanks. I want to ask that when we use indexes to denote a plan, are
we
we
use-
referring to a series of parallel planes, or are we just referring to one?
When we use the index, which index? I'm sorry, you mean like this in this equation?
It's a question from last course.
I'm
Like-
sorry. Wait. I'm sorry. So are you asking a question about today's lecture or something?
No,
different?
from last time's lecture.
Oh, so okay, it has nothing to do with today's lecture. Okay, well, in that
Yes.
case, let me stop sharing the screen. Okay.
Okay, sure.
I want to stop sharing the screen. Stop share. And then I want to stop the recording.